So now we finished defining the physics number one. I can move on to the mesh node. There's always going to be a default mesh. If I click on build all, it'll build me a mesh. And I could actually look at the details by right click and edit physics induced sequence. So in this case, this particular free tetrahedron mesh was generated with the sequence with some predefined level of normal. You could further refine it or make it coarser. You could also more accurately control it via the custom option and define what's the maximum, minimum mesh size, and also what is the growth rate and curvature. If there's a narrow region, how many layers on average you want to have in terms of mesh in that narrow region. So in this case, it's a uniform size everywhere in the entire domain. But of course, we know that's not always the most effective way or efficient way of meshing. For example, if you do have a high gradient close to a certain surface, we know that there's a lot of, say, like electric double layer in that region, and the concentration gradient is really high. Then what happens is you do want to further refine the mesh close to that particular surface. So in that case, I could add a size node under the free tetrahedron and choose the size node to control on the boundary level. So the levels here are domain 3D, boundary in this case is 2D and 1D and 0D for the edge and point. Of course, you have a different definition of domain when you have a 2D geometry. Then the boundary is actually an edge. So in this case, we're going to say I want to refine the mesh close to this boundary number 1. I want to use the extra fine mesh here. So you see that the mesh around the surface is actually refined. Of course, you can see it even better with the further refined. And then you can change that mesh size node as well. And this is the mesh number 1. If you do say, I know this geometry is actually an extrusion geometry, so it has the same thickness everywhere. What if I want to use a different mesh type? So you can right-click on the component 1, add a different mesh. So now you have mesh number 2. Say I actually want to use a free, let's do a free triangular mesh on the side surface. And then I could add a swept mesh for the domain. And for the sweeping, I want a distribution of 10 layers. So why is this useful? So if you do have a high gradient in the y direction and less gradient in the x and z direction, so this way it allows the mesh to be element to be still very reasonable, only 480 domain elements. But meanwhile, you have much better resolution in the y direction. So if there's a high gradient, you can resolve it. And also, when you have a very thin structure, then you do not want to use too fine a mesh that's confined by the smallest dimension you have. In this way, you can actually mesh the thin structure fairly well, and meanwhile keep the mesh element size and on the other dimensions reasonable. All right, so just the other mesh options, of course, are available through the right click of the mesh as well. So you see, for fluid flow, one of the very useful features is a boundary layer mesh. So especially when turbulence happens, you do want to resolve the wall regions, the close to the wall, very finely. So that's when you can define the boundary layer mesh and specify how many layers you want, how much do they stretch per layer, adjacent layer, and then what is the initial layer thickness. So it is actually the default option when you have a fluid flow physics, and the default mesh controlled physics would have the boundary layer added already. All right, so that's about the mesh. Then we can look at the study. So right now there is a study step 1 stationary, and it's going to solve for the electric current physics. If you do want to look at the solver settings, you can show default solver. We can expand it and see that's the dependent variable we're solving for. We know that in the model wizard, the component 1.v, uppercase V, or just directly uppercase V, that's the electric potential. It's a stationary solver we're using. There is a relative tolerance that's being specified here. There is you can whether to show the results while the solver is moving, so that's actually useful when you have a longer computational time and you can see what's the current solution without waiting until the end. There's let's see what other things you need to know. The fully coupled solver is the one that's being used right now. It's using a linear solver of iterative solver, and more iterative solver details right here. It's a multi-grid solver with some pre-smoother, post-smoother, and core smoother. So most of the time, you don't have to change the default solver, especially so far as you know this is a linear problem. So we know already that it's going to solve in one iteration. all linear problems solved in one iteration, because you go down the tangent and you go through the straight line and you find that solution or error estimates to the minimum directly through that one iteration. So it's a MUMP solver that's being used now. The other direct solver includes the Palliso, spools, and dense matrix solvers. And let's see what else. So basically, a lot of times you do want to, and the nonlinear method is a Newton iteration, Newton-Raphson iteration. So you already know that. Let's see. So I would say the tolerance determination technique right now is by default is set to be tolerance. So basically, you know, you can choose between tolerance or iterations. So it either, for example, terminates after 25 iterations or when the tolerance criteria is met. So the two concepts here is the relative tolerance and the absolute tolerance. So the looser of the two is going to be in effect. And then when you do want to refine the solution, you do want to refine, for example, type of extra zero here, you know, to tighten the tolerances. But of course, that comes at a cost of more computational cost. So it's always a balance between the two. So in this case, we all know it's going to solve. So we're going to right-click on Study 1 and hit Compute. So here it shows the progress. And here it shows how much physical memory and the virtual memory that's in use. And now we solve for the electric potential, how it distributes. By default, comes already generated a plot group for me. Just to show you how this works, you can always right-click on Results, add a 3D plot group. And in the 3D plot group, you can add any type of a plot that you think would be able to nicely visualize this. For example, instead of the slice plots, the multi-slice plot, I could do a single slice in the, let's do XY plane, actually a YZ plane, and just one slice. So this is how the potential looks like in the cross-section. I could make the slice interactive and basically just scan through the geometry to see what is the local potential distribution. You could also do like just a cross-section XZ plane of one slice. So that shows you where the potential goes from 0 to the other end, the highest end, 0.2 volts. On top of the slice plot, you could also add, for example, an arrow volume. So I'm going to use the arrows to show how the current flows. So I'm going to use maybe 20 points in the X direction, just 1 point in the Y direction, and 10 points in the Z direction. So now I have the arrows flowing from the high potential end to the low potential end. The direction of the arrow, of course, that's where the density goes, the current flows. And then the length of the arrow is actually proportional to what is the local density. There is some singularity around the shoulders because of the sharp transition. Electric currents cannot make a perfect sharp turn because of the divergence has to equal to 0. So you can also, for example, add on top of the arrow volume a color expression. Say use the color to represent what's the current density. So you can type in a replace expression and find the current density norm. So now the color actually shows what's the magnitude. You can change the color table so that it doesn't mix with the other one. So different visualizations you can do. Any questions on what we have done so far with the single physics problem? All right.